This video tutorial will present an example of a two-way slab in Adapt PTRC for the purpose of an existing evaluation. So we want to model a slab. We're going to show the input of segmented geometry, how openings or a reduced section will be handled within the program. And we're going to do this with both post-tensioning cables as well as base or user-defined reinforcements. So we're going to be using Adapt PT20 for today's example, and this version will be released in March of 2021. Let's go ahead and get started. We're going to select a new file, and we'll just set up just an arbitrary example. We'll draw a small sketch here to kind of show what we want. So we're going to do a 3-span condition, something like so, columns below only. And if I kind of flatten this out in plan view, what we're going to have is a prismatic span in span 1. Span 2 will have a prismatic span. And then in span 3, what we want to do is we're going to say that originally this particular strip was also the same width. We'll call this W here as span 1 and span 2. We'll call this middle span. But there may be a need to puncture the slab, put a new opening in, and then we need to determine the new capacities for the section. So we're going to say that the opening will be here. Okay, there's the opening. However, when we model in PTRC, what happens is if we have our columns set here, so these columns are shown there, everything is done about a center line. So we have this datum or center line that we're referencing. We'll call it a reference line, RF, or excuse me, RL, reference line. And so we cannot model an opening away from the reference line. In other words, I couldn't puncture a slab here where there's a gap between the reference line and the face of the opening. So to do something like this, what we would have to do, and I'm going to just draw this second bay here, we would actually do something where we would create something like that, where this is the width of the opening, this is the length of the opening this way, or vice versa, and this particular segment, we'll call this segment 2. Here's segment 1, segment 2, and segment 3. Segment 2 is actually bound by the reference line. So that's how we need to consider the openings. We're going to show segmented geometry. It's really all or nothing, so I can either do conventional geometry, which is prismatic for each span. They have to have the same width in each span, same thickness. You could have offsets vertically, so this technically could drop down if you had an offset slab. If you go to segmented, all of the input has to be segmented. So we'll show that here in the input. So we're going to select two-way slab. We're going to go to segmental. Once you select segmental, notice that the ability to just create drop panels and drop caps automatically just through input of their geometry goes away. You actually have to build those out through the segments that you include in the span. All right, so recommended slab thickness, we'll say no, we don't need that. We already know what the slab thickness is. Keep in mind that when we're using this program, the program is really always working in a new design mode. Even if we enter base reinforcement and post-tensioning that we know is in an existing slab, the program will actually tell us what additional reinforcement we need. But we also have the ability to produce as-built or existing moment capacities against the demands. And that's something that's important when we're doing an investigation. So if we go into this next option here, you can see there's analysis settings. I'm not going to go into the details of all the selections. We have another video that's just a pure tutorial of the program, but we're going to point out what's really necessary to do an investigation. So one thing that is necessary is this option here. If you select design values, then the FEMN, for example, is going to be based on the user-defined reinforcement. So that's existing in the slab, plus PT, that might be existing, plus calculated reinforcement. And this is the big one here. If the program determines there's a need for additional reinforcement to meet M sub U, then it's going to add that, and the capacity will be generated based on all three of these components. If you use user entered values, this is really what you want to use for an existing slab. We're only looking at these two, user defined rebar and the PT. So for investigation, use this option here, user entered values. Okay, so we'll select that. And let's go ahead and set up the geometry. We're going to add 3 spans. Okay, we have 2 spans we're actually going to say are prismatic. The other span is non-prismatic. So we'll say that these spans are all just 30 feet just to simplify the geometry here. Okay, for the prismatic spans, we can enter the data directly in this table, the span geometry table. So we'll say that the width of the slab, let's just say that's 300 inches. And then the height of the slab, we'll say these are 8 this is an 8-inch slab. The reference height I like to set equal to the height of the slab. That way all of my control points for my PT, if I have a PT cable here, they're all referenced from the bottom up. This is the reference plane, or the reference line here. If you leave the reference line set to 0, it's actually up here, and all of the points are referenced downward, so they're all negative values. So keep that in mind. This kind of gets grayed out here because we have to fill in the sub-segments. So if I zoom out, you can see that the end span, the two end spans will be produced graphically because those are set to prismatic. You could also set them to non-prismatic and build out additional data for that. But if I go to more, what's going to happen is this allows me to fill out sub-segments. Now the first sub-segment is actually going to be half the distance of the column. So I'm going to exaggerate this. Let's say this is our column. Segment 1 will always be this distance. So it's going to be half the dimension of the column. And the last segment will always be half the dimension of this side. So this is segment 1. In this case, this is segment 3. That means between these two segments, 1 and 3, we only have one additional segment. So I could only reduce, or define specific geometry to one additional segment. If I wanted to break this up, let's say I have that opening kind of in the middle of the span, I'm going to need actually 5 segments because I need to be able to input geometry here, here, and then in this last segment within the 2 supports. So let's go out of this dialog just for a moment. We'll just escape out of that warning. And I'm going to actually input the column dimensions first, and then I'll go back into that input. So we're going to go to lower column. I'll say these are 10 feet in height. And the dimension B is actually transverse to the span direction. So we'll say that's 20 inches. And we'll say this is 24. So half the span, half the column width in the direction of the span is 12 inches, 1 foot. So segments 1 and end segment will be both 1 foot. If I go back and go to more, I'm going to bump this up like so. And we're going to say that there's going to be a segment. Let's say this is 1 foot. So we'll say there's a segment at 10 feet and at 20 feet, like so. So this is actually segment 2, 3, 4, and then the last segment is this one. And you can see segment 1 goes from 0 to 1, so it's actually 1 foot. It starts at 0, goes half the distance of the column, and then this one starts at 29 and goes 1 foot. So let's say that if we go here to XL, we're going to say for segment 2, this is going to start at, let's go here. This is going to start at 10 feet, and this is going to start at 20 feet. Okay, so we have 2 additional segments, and we can now input the geometry. Now if I go to the typical row, and I'm just going to say all of the widths are 300, and let's say all of the depths are 8, and all of the reference heights are 8. If I look at this in plan, you can see the subsegments. Now I want to take away from this second, or this is really the third segment, I want to take away some dimension here, and maybe I want to take away here. Maybe there's an opening in this real slab here, and there's an opening here, and those two new openings are cut into the slab currently. So we're going to say that we're going to take away 100, and we'll take away 100 here. And so let's go ahead and do that. So the second segment is actually going to be just 100. So we'll go to segment 3, or the third segment. This will be 100, and you can see that I cannot have a situation where there's slab here, this is filled in, slab here, and then this is open. This is not supportable by a frame, equivalent frame based program adapt PTRC. It has to be bound into the reference line. So this is how we're going to model that. And once that's modeled, we can select OK. We have our geometry now, and we can continue on. We've already entered the supports. We have support conditions. Right now, these are just fixed at the base. Loading. I won't go too deep into loading, but we're going to turn off skip loading for this example. And we're going to say that for all of the different spans, let's say spans 1 and 3 have the same level of loading. Okay, and we'll say that the live load is 40 PSF and the superimposed dead load is 15. And then for span 3, we have something similar. By the way, self-weight is auto-calculated here. If you want to enter self-weight directly, you could turn that off. And then when you go to a classification, you have another load entry there for self-weight. So we'll have the program auto-calculate self-weight. Now for span 2, we're going to do something different. We're going to say that for live load, we're going to actually use a line load for both of these. And we'll say for some reason, because these openings are here, there might be some stairs that are kind of coming up into this slab, and they're putting a line load here and maybe here. And those line loads are actually going to be represented on the center line, the reference line of the frame. But we'll make all of the loading for span 2 equal to a line load within this realm right here. I'll talk about this segment and this segment here in a moment. But for this internal segment, we're going to do something a little different. So we'll say that the line load there for live load, we'll say it's 2 kips. For superimposed dead, I'll say it's 3.5. This is kips per foot. And we'll say that that start of the line load will be 10 feet, and that'll end at 20 feet, 10 and 20. You can see that's only over that interior portion. And then for I need to make sure that this is in span 2. Okay, so there's the 3.5 and the 2, and then I have this will also be in span 2. So I need basically 4 more entries here. We'll do live load, super dead, live, and then super dead. If I just select U, the second description, this is per alphabetic description. So L is basically load uniform, load partial, load concentrated, etc. So if you use the second descriptor here, you can get that load type entered into the matrix. So the first thing we'll do, actually we're going to do partial uniform. I put in the wrong character there. Okay, we'll say that this is 0.04, 0.015. You could also copy paste in this table, and again this is going from 0 to 10. This is from 0 to 10, and then this one here is from 20 to 30, 20 to 30. Okay, and that fills in those gaps in segments 1 and 2 of span 3. Or actually segments 2 and 4, because the first segment is actually this starting segment, but this load that I've entered actually covers the first 2 segments and the last 2 segments. All right, so that's the loading. We have material entry for the materials that you want to define, both for concrete, reinforcement, and then also for post-tensioning. So as the user determining what kind of tendons you're going to use, you want to make sure you correspond the input here with the type of tendons that have been used in the as-built condition, because we base the calculations, for example, for strength off of these properties. So make sure that you fill this out properly. It's important to note that the effective stress that's assumed here, if we're going to use effective force method, is going to be used as a basis for calculating the strength that's derived from the PT. So make sure that you have a proper input here. For an existing condition, this may require some assumption, conservative assumption on the basis of the user. So make sure you pay attention to that input. Base reinforcement. Let's go ahead and look at this. So for base reinforcement, we basically have two types. We have mesh and isolated. So if you had a uniform mesh in this in this slab, let's say at the top or bottom, we could enter that uniform mesh, or you can enter discrete bars. I'm going to show an example of both. So we're going to say for the bottom of this slab, there's a uniform mesh. I'll go to mesh, and I'll say the first end location is going to be at this support. So we'll say that that's in span 1, 0 is the ratio of the start point to the span length. That's just right at that left side column. The second end location, it's going to go all the way to the end. And we'll say that's in span 3, and x2 over L is 1. So we're going from, we're taking 100% of this span length for that ratio there. And then for the bar size, we're going to say these are number 5s. Spacing, this is the transverse spacing of the bar. We'll say that that's 12 inches. And these are going to be bottom bars. The cover, I'll say, is 0.75. This is cover to the longitudinal bar, the outside face, in the direction of the span. For isolated, we're going to put isolated bars only over columns. So we're going to have 1, 2, 3, 4 isolated inputs. And you can always stretch this down. I could stretch this down as well. So we'll enter 4 isolated bars. The first end location will be span 1. This is going to go 0. Second end location will be span 1. We're going to say that this bar goes half the distance in span 1 at the top. Bar size, we'll use 5s again, and I'll say there are 4 number 5 bars, top bars, and we'll say the cover is 1. So we'll use the same cover here. These are all top bars. We're going to use the same quantity and the same bar size. Okay, so the second entry, actually let's say that this is 0.35. So the second entry will be in span 1. This is going to be at 0.65. Second end location is 2, and that will be 0.35. And then we'll kind of repeat that pattern. We'll go, the first end location here will be 2. We'll see that's 0.65. Second end location will be 3, and that's 0.35. And then the last one will be in span 3. This is 0.65, and this is 1, like so. Now you can see those bars, at least the isolated bars. If you go to a wireframe, there are the 4 bars in each column location. Okay. So the mesh reinforcement doesn't appear in this view, but the isolated bars do appear. Okay, once that's done, we'll go to next. The criteria for allowable stresses, this is really for new design, so we're just going to go bypass this. When we're trying to design the PT for this slab, for example, for new design, these are the targets that we're trying to obtain and the permissible stress envelope, if you will, for the design. So we'll just leave that set to default. These are also target criteria: pre-compression, balance loading. Again, I'll set that to default. We're going to use force method for the tendon. We're going to assume kind of a lower bound force, effective force in the cables after all losses. Again, for new design, the user could use force method, or we could calculate the varying force along the cable length due to the losses. Profile, if the tendon shape is known in the existing slab, you could set up your spans with that particular cable. So this is tendon A, B, and C. Tendon A in the program is always from end to end, so you might have this cable. Tendon B might be an add cable from this end here. Tendon C might be another add cable here. So these two cables, B and C, are typically used for add tendons or add cables. We're going to assume that the profiles are just the defaults, reverse parabolic, that's type 1, and the inflection points are set here as a function of the span length for the particular spans. The option for tendons here, this really relates to the add tendons. How do we anchor the add tendons? If they're, for example, 20% of the span length behind a support, how do those get anchored? Are they anchored at centroid? Is it a fraction of the span? So by default, it's 20%. You can modify that in the when we get into what's called the PT recycler window. Okay, so once that's done, we can go into cover criteria. This is really for new design. This doesn't really affect an investigation. This is only for new design. This is also for new design in terms of the reinforcement, curtailment, and cutoff lengths. So we'll kind of skip past those. And then we get into combinations. Which combinations do we want to evaluate for our design? Now, for existing design, we may only look at strength. We don't really care about the service combinations unless we're evaluating deflections also. Then the program's producing deflections for these combinations here. So we're ignoring the new design component of what we're going to run where the program will actually show us the new reinforcement. We're really worried about that demand capacity check. Once you've entered the input, we're going to select the option to save the file. So we'll go here and just save this. All right, and we're going to assume that for this particular slab, this might be a banded run. So all of our cables are kind of along the center line. That may have limited them actually cutting out or cutting further, let's say, into this zone. We need, let's say 2.5 times the slab thickness or some requirement of distance, away from the edges of this band, this existing band. So that's why we have this throat that we're kind of working with here. And ultimately, once I have entered my input, save the file, I'm going to go and I'm going to actually run the execution of the file. And this is, again, this is looking at this as if it's a new design per all of our input, but we're going to tell the program what the actual post-tensioning force is and what the profile is. There are 2 entries in what we call this PT recycler, and those can be modifiable. So currently this program PT recycler will dictate what it thinks the force needs to be for this design as if it's new. And it's come up with a force here of 608.4. These heads-up display options are really for new design. They're telling the user whether you meet or exceed PT pre-compression, balance loading, or the stresses. So I'm not really paying attention to this either. I'm just going to go in here and say I know that in the slab, as-built slab, there are only 18 strands. So here I have this option for strands, but I cannot override this. This is read-only. These strands are a function of the force. So to get 18 strands, if I know that my effective force input in the input screen was 175, if I take that times the area of the cable, 0.153, I get an effective force of 26.7. So if I take 18 strands times 26.7, I'm going to actually enter a force here of 480 kips. And this, in essence, equates to 18 strands using an effective force of 26.7. So I also know that the as-built condition actually shows the, let's say, the outer bay control point or low point as 2.5 from the soffit up, and maybe the inner bay as 1. Let's say 1.5. So once I update these numbers to reflect what I have in my existing condition, I'm going to recycle. And you may see that some stuff doesn't work. For example, based on this input, if this was looked at as a new design, and also based on the input that I made prior to coming into Recycler, my stress doesn't work. I'm actually overstressed. The allowable is 6 square root of f prime c, but this is telling me my stress is 10.5. So this might be useful information for the user to say, oh, with only 18 tendons per this modification to the geometry, my stress is too high. Also, and that would also be impacted by the loading that we've input. And also the P over A is really high. It's 600 psi because I've now produced 2 penetrations in my slab, and I've taken away some of that concrete that's currently in the slab. So this again is intended really for new design, but it can be useful when we're looking at the current stress condition of the slab. So once you've modified the force, the profile per as-built conditions, then we're going to exit. And when we exit, we're going to go directly to really the main result that I think users are looking for when they're doing investigative slides within the program, and that's under the report generator. If you go to this detailed report option, and in the detailed report option, we're going to go down here to demand capacity, this one right here. We're going to produce that report. Okay, and this is what that report looks like. For each span, we have 20 points set up, and it shows us those ratios of the span length and the actual distance from the support of the span. We have our demand moments. These are positive, negative. Our moment capacities, positive and negative, and our DCR is positive and negative. So the user could look at this and determine where you exceed requirements. For example, negative capacity here at the first interior support, kind of this bunch right here exceeds, this is greater than 1. And so per the reinforcement, the 4 number 5s that I entered, this is not enough capacity. This also includes contribution from the PT as well. And that's probably symmetric due to the symmetry in the model. But this report is, again, a user-defined report. It says capacity is calculated with user-entered rebar and PT. And if the user wants to know what reinforcement is required to actually meet demand, then you also have that option. We could go here to the what's called the builder sum summary report, and for example, for strength, strength 1 and strength 2, let's go to strength 1. If I produce that report, the program reports the amount of rebar we need in addition to what I've already added into the model. And this actually has a lot of need of rebar, 11 number 5s at both of these interior supports in order to meet the capacity needed for this design. This is what would be required in area of steel, more decimal format, numeric format. These are the areas required to meet the demand. This is in addition, again, to the user-defined rebar and the post-tensioning. So that's only for strength 1. If you look at strength 2, then this is a separate result. So here we need 7s. This is 1.4 times dead load. The other is 1.2 dead plus 1.6 live, and this shows us similar results. Minimum requirements may not be required. Service, this is really for minimum rebar, and if the slab has already been built, then it's assumed that the reinforcement in the slab meets the minimum reinforcement per the code that it was designed under. If you're trying to bring this up to code, then you may want to compare, the results of the service requirements in addition to strength, and you could do those using the envelope, for example. This shows me more of an envelope result, and this is still that need for strength required rebar at these 2 supports. You can see out on the ends 0.57. Those are top bars, also 2 number 5 tops. Those are coming from the service condition. So for a two-way PT slab, there's a need for 0.00075 area of concrete in either direction, and that's coming from that condition. There are also punching shear results as needed by the user if you have a need for determining the punching shear within a slab. You could do that also. Let's go back to this result here. And for punching shear, the user may be interested in the compact report 13 or the detailed report 30 for punching shear, and the user could produce again these results in tabular format, and this kind of gives more information on the condition and the requirement for each particular column. So you can see the stress ratios are pretty high here, and this is actually showing us reinforcement for these columns. So if the existing punching shear reinforcement doesn't meet this requirement here, then it would be insufficient. The user would then be able to take this information and determine what might be required in order to satisfy the current demand based on the penetrations in the slab. There's additional detailed reporting here. This kind of goes through every layer. So at a particular column, the program is checking critical sections away from the face of the column at D/2, D/2, and so on. And these are those different layers with the stresses that it's checking and the required area of steel between each layer. If you have any questions about this process or about the program ADAPT PTRC, please contact us at adaptsupport@risa.com. Thank you.